So I wanted to give you a hand with problem 3. Looks like we have an antelope moving with constant acceleration who covers the distance between 2 points that are 80 meters apart, and it takes the antelope 7 seconds to cover those 2 points. Okay. And its speed as it passes the second point is 15 meters per second. So I think this is screaming for a velocity graph. So let me start there with a velocity time graph. And the hard thing about this problem is people don't realize that it doesn't say anything about the initial velocity. So we don't know what the antelope's initial velocity is. I guess it could be 0, right? So it could be this. It could be some positive velocity. Or I suppose the antelope could have an initial velocity that's less than or greater than the final velocity. So you've got several possibilities. I'm just going to call the initial velocity v because I don't know what it is. All right? And then it's pretty easy to see that the time we're talking about here is 7 seconds. So let's see if I can make this 7 seconds. And let's see, what else can we figure out? Well, we know the ending velocity is 15 meters per second. I'm going to try to simplify my life by having the antelope start, there's my antelope. You have to be a really good artist in physics, so there's my antelope. I'm going to start my antelope at 0 position, and I'm going to have my positions in meters. And I'm going to have my antelope going in the positive direction, which gives me my positive velocity of 15 meters per second. Again, this is meters per second at the end. And I'm going to call the beginning velocity just v, because I don't know what it is. In fact, I could call it v naught for velocity at 0 seconds. That might be nice. Now, you have a choice here. You can solve the problem just by looking at this as a trapezoid, or you can solve the problem by looking at this shape as a rectangle plus a triangle. Either way will work fine. But the total area of this velocity graph, by now you should realize that this area is going to be measured in meters, and it's going to be the displacement of the antelope. So whatever this change in position is, that's what that area is. So looks like that's 80. So we've got a change in position of 80 meters. And let's set up our equation. Let's use our velocity graph to set up our equation. So I have 7 times my initial velocity for the antelope. That's the rectangle right here. Okay? So that's area of the rectangle plus the area of that triangle. Now, this amount here is going to be 15 minus my initial velocity. So I got 7 times 15 minus initial velocity, right? And I have to divide that by 2 since that's the area of a triangle. And together, these will add to 80 since that's my displacement. So now, see what, it's just algebra. So 7 v naught plus, 7 times 15. I'm not sure what that is. So let me try the calculator. Okay. 7 times 15, and I get 105. okay? But that's divided by 2. So 7 times 15. Well, I'll break this down in steps, okay? I'll divide by 2 later. So that's 105 minus 7 times V naught, okay? And both of these are divided by 2. And that has to equal 80. Okay? So I got 7 V naught and 105 divided by 2. Let's see what that is. Divided by 2. That's 52.5. So plus 52.5 minus, now this is going to be 3.5 V naught, has to equal 80. Okay? And 7 minus 3.5. So since both of these have V naught, we can subtract them, like 7 apples minus 3.5 apples. So that makes 3.5 V naughts. And this is going to equal 80. And now I'll subtract my 52.5 from both sides of the equation. So 80 minus 52.5. Not sure what that is. Might as well calculate that. 80 minus 52.5. And I get 27.5. So now let's see. I get 27.5. And this is equal to 3.5 V naught. Alright. And it looks like I'm almost there. I just got to divide both sides by 3.5. And now would be a pretty good time to check my units. Going back up, this 80 is meters. So when I subtract 52.5 from 80, that is also in meters. That means this number is in meters. Now, 3.5 must be in seconds. And if I look up here, my 7 right here was in seconds. That means this 7 was in seconds. That 7 was in seconds. This is in seconds. This is in seconds. This is in seconds. So this number is in seconds here. And that means that this 3.5 is measured in seconds. So when I divide both sides, my units are meters per second. And this shows that since I'm finding an initial velocity, that totally makes sense. So I'm pretty sure this answer is going to be correct because I checked my units. Divided by 3.5, and I get 7.9 roughly. So that's 7.9 meters per second. So I found the initial velocity was 7.9 meters per second. And that means this graph was correct. I just guessed. It didn't seem like the antelope was slowing down. And it didn't seem like the antelope started from rest. So actually that graph in the middle was the correct graph. Now I wonder what else we could find here. This is the speed of antelope while crossing the first point. Which is pretty cool. And you could go further with this problem. You could easily find an acceleration now. Maybe I should do that. So acceleration of the antelope is going to be the slope of this velocity time graph. And the final velocity was 15. The acceleration graph looks like this, right? And this was 7 seconds. So t is seconds, and this was 7. Okay? So acceleration is going to be our change in velocity divided by a change in time. I go back to the previous page. I can see my beginning velocity was 7.9. I'm just going to call it 8. My final velocity was 15. So I'm going to take my final velocity and subtract from it my initial velocity. Take my final time minus my beginning time. Okay, so 15 meters per second minus 8 meters per second, and that's going to be over 7 seconds minus 0 seconds. So that should give me an acceleration of basically 1, because 15 minus 8 is 7. So we got a change in velocity of 7 meters per second. That takes place every second. And this would be a great time to try to translate what you have into simple words. Every second, Antelope in this problem speeds up by about, this is actually 7 seconds here, which means our acceleration was 1 meter per second faster in 1 second. There we go. Now it's cool. Every second the antelope speeds up by about 1 meter per second. So again, the 1 meter per second is the change in speed that's happening each second. Anyway, hope you like that problem. Hope it helps you understand a little bit of physics. And wait a second. Couldn't I find more here? Look at this graph. Oh, we already know how far it went, so we cool right there. That was 80 meters. All right. Anyway, thanks for watching. Hope you have a good day. Bye-bye.